This lesson is 2.2 in the textbook, and it's called the square root of a function. We're not talking about y equals root x. That's not what I'm talking about here. Y equals root x is the square root of x. I'm talking about the square root of a function. What we need to be able to figure out today, and it's a very simple idea once you see it, is what's the relationship between the graph of a function f of x and the graph of a function root f of x? Well, first of all, what does that even mean? What it means is if you know what y equals f of x looks like, whatever f of x might be 5x plus 8. Then the question is, what does the graph of the square root of 5x plus 8 look like? Okay. Now I realize that if I said, what does the graph of the square root of 5x plus 8 look like, you can put it in your graphing calculator, but you also know by now that questions are designed so that you don't know the equation of the function necessarily. You might just be given a graph. So this is the goal. Let's say you have information about the graph of y equals 4x minus 11. The question is, what does the square root of 4x minus 11 look like? If you have information about the graph of this function, what does the graph of that function look like? So in general, we're saying if you are looking at a graph of a function, and I say, what does the graph of the square root of the function look like? That's our goal today. And again, it's a simple idea when you see it. To begin with, though, let's talk about square roots. When are you allowed to take the square root of a number? Well, you're only allowed to take the square root of a number if the number is 0 or bigger than 0. You cannot take the square root of negative numbers in high school math. And I say it that way just because there's another branch of mathematics that deals with something called complex numbers, where you can take the square roots of negative numbers. They call them imaginary numbers, which is a bad word because they're not imaginary. They're real in the sense that we can use them, but they're not in what we call the real number system. This is something that I never really realized until I actually had to teach something like this in high school. I always assumed when you took the square root of a number, you got a smaller result. I always thought that was the case. Like root 25 is 5. It's smaller, right? But that is only true if the number you're taking the square root of is bigger than 1. See, and I can see the looks on some of your faces. You're going, really? Yes. I mean, convince yourself. Take the square root of 2 on your calculator. The fact of the matter is 2 is a number that's larger than 1, and when you take the square root of 2, you get approximately 1.4 something. You get a number that's smaller than the number you started off with. But it turns out when you evaluate the square root of a number smaller than 1, now wait a minute, but if it's smaller than 1, it must also be greater than 0. This is what I'm talking about. If you evaluate a number, a square root of a number between 0 and 1, it turns out the number increases. So for example, if you take the square root of 0.5, I believe you're going to get 0.707 with more decimals because it's an irrational number. And then if you evaluate the square root of 0 or the square root of 1, you get the same number. And I could have written the same number, but I want to use the word invariant. So whenever you square root 0, you're going to be still at 0, and whenever you square root 1, you're still going to be at 1. And this can be summarized by that number line I've given you, that these numbers up top are values of n, and
sorry for the interruption. Mr. Wilmot, please contact the office. Mr. Wilmot, please contact the office. Thank you.
And the bottom that I'm going to put in blue is going to be the square root of the number up top. So what do we know? We know that any numbers over here are not defined as square roots. We know that if you take the square root of 0, you're going to get 0. If you take the square root of 1, you're going to get 1. You get a larger result in here, and you get a smaller result in here. And this will be important for when we sketch graphs of the square roots of functions. So example 1, we're going to go through, I think, 4 examples here today. Example 1 is simply, it's not even actually an example or a question you would see on an exam. It's something that I've come up with to try to get you to understand what's going on with square roots of functions. So a function is described by f of x equals negative 2x plus 2. Does that match your function? Okay. And I've given you a table of values for the function. Here's the table of values. So what I've done is I've just picked some numbers, and don't worry about why I've picked this 0.5 in here. I've picked negative 4, and I put negative 4 up here for x, and I get 10. And with a little bit of thought, you can convince yourself that you could find these numbers as well, these y coordinates on the graph that correspond to those x coordinates on the graph of f of x. And the question says, write the equation of g of x equals root f of x and complete the table of values for g of x. Well, if g of x is root f of x, and f of x is negative 2x plus 2, then g of x is the square root of negative 2x plus 2, right? But that's not even a Math 30 idea. I'm just saying we're taking the square root of the old function. So let's complete the table of values. And I would like exact results here. So if you end up with the square root of 7, and you're probably not in any of these, if you end up with the square root of 7, then you need to write root 7. So I'm going to give everybody a minute, and your job is to use the information up here to fill in these numbers. And when you have them filled in, I want you to put your hand up and then down. And those people that have it done are not necessarily done because they're brilliant. They may be brilliant, but they're not done because they did a whole bunch of calculations in their head, I don't think. They're done because they recognize, everyone, that this under the square root is this. This is the most important part about today's lesson. The y coordinate on a point for the square root of the function will be the square root of the old y coordinate. I mean, if I put negative 4, in here, then I'm going to get 10 under the square root because we've already established that's what negative 2 times 4 plus 2 is. So you could put these numbers in, or you could use this idea and say, well, this must be root 10. It has to be root 10 because what's under the square root is the number that corresponds to the y coordinate over here. And this has to be root 8. Ugh. So this is root 10. This is root 8. Now, I don't want to get into it. You could simplify root 8 and write 2 root 2, but I don't care. That's not an important point in this lesson. This will be root 6. This will be 2 because it's root 4. This will be root 2. And here's why I chose an x-coordinate over here on the original function of 0.5, because I happen to know the y-coordinate of that point is 1. I've looked ahead and I've said, oh, where is y 1? And that's going to be important because the square root of 1 is 1. And what this means is that this is going to be an invariant point when we compare the original function to the square root of it. An invariant point will exist if the y-coordinate on the original function is 1, because we're taking the square root of y. It turns out, as well, that since at x equals 1, the original function, which is under the square root, has a y-coordinate of 0, the square root of 0 is still 0, so that will be invariant as well. We're learning something very important here. any place on the original function y has a value of 0 or 1, we will have points that are invariant on the square root of the original function. And then, of course, here, undefined. And the second important, well, it might be the third important, I've said a lot here. Another important point is that the square root of a function will be undefined whenever the function is negative. And when I say function, I mean y. So what have we learned from this little exercise with the data tables? It says explain the relationship between a point on the graph of f of x and the coordinates of a point that correspond to it on g of x in this circumstance. In other words, how do the coordinates of f of x compare to the coordinates of root f of x? And I'm simply going to, I'm not even going to use g of x here. I'm just going to say this is the old and this is the new. And we will not explain it in words. We're just going to write the mapping now. What is the mapping? The mapping is this. That's it. That, in a nutshell, is the lesson. Really, that's it. That if you want to find sister points or plot a corresponding graph for the transformation of y equals f of x to y equals root f of x, the mapping is this. Okay? So, using that knowledge, if you were asked, not even knowing the equation of this graph, like this is y equals 2x, negative 2x plus 2. But if I just said to you, here is a graph of a function, what will the square root of that function look like? You will say the following. You will say that this point, and this point will be invariant. Because that's where y is 0 and y is 1. We're looking here because that's where y is 0. That's your eyeball. And we're looking here because that's where y is 1. And any place that original graph is on that horizontal line, that's the x-axis where y is 0, or anywhere that original graph is on the horizontal line at y equals 1, those will be invariant. And then we can pick some key points. Forget about the table. I can just take, well, this point right here. On the original function, this point on the original function has a y coordinate of 4. So I take the square root of 4, which is 2, and I say, oh, this is going to be down here at 2. I can take this point, which has a y coordinate of 2, and I take this square root. We need to use decimals here to find out where it is. I know it's going to be at root 2, but what's root 2? Well, it's 1.4-ish. So this point is going to drop down to about 1.4. We can take, at least 2 more points to add a little texture to this graph. You might want to take, here's a good idea, forget about the data table, let's take this point, because that point has a y coordinate of 9, and I know the square root of 9 is exactly 3. So I want to keep, everybody, the same x coordinate. I just want to drop this down to 3. I just want to drop this point down to 3. That's close enough. I mean, we're not landing people on Venus here. It's good enough. But there's a very minor thing, and you will have more success at drawing this properly than I will. I would like everybody to take this point, say here, which has a y coordinate of 0.5, and take the square root of 0.5. You get 0.7, roughly. So you get a number that's a little bit higher. And in this band between y equals 0 and y equals 1, all of the y coordinates are numbers that when you square root get bigger. So the square root of the function in between where y is 0 and y is 1 will be higher than the original function. But over here in this region, the y coordinates are numbers bigger than 1, so it drops off. So when you draw this, my computer sometimes locks up for a minute when I do this. So I'm going to take a chance anyway. Well, I did it okay. I'm going to go to 300%. And what your graph is going to look like, and again, you will have more success at drawing this on a piece of paper, and so would I. I just can't draw curves on a vertical surface very well. I'm stealing myself up for doing this properly. It's going to come up and over, and I'm going to stop there because I did a pretty good job and I don't want to mess it up by including more stuff. There's just some important things I want to go over here. All you do is you take a bunch of points, every point really, but you don't need to do every point. You take the square root of the y coordinate and replot it with the same x coordinate. Any place above where y is 1, the graph drops off, it gets lower. Any place between y equals 0 and 1, the graph grows. Any place where y is 0 or y is 1 is invariant. And lastly, any place the original function is negative, the square root function does not exist. This is hard for me to communicate with a diagram, but I'm going to do this. Right? It exists at positive 1 because the y coordinate at positive 1 is definable. The y coordinate is 0 and the square root of 0 is 0. You can plot it. But everywhere to the right of positive 1 on the original graph is below the x-axis. The y coordinates are negative, which means everywhere to the right of positive 1 on the square root of the function, there's nothing there. All right? Does anybody have any questions with that entire example? So far? No? Okay, let's take a look at example 1. Did you have more at the bottom of this page on page 47? Can I see yours? Identify the invariant points by circling them. Explain why they're invariant. Okay, I forgot to do that. I don't have that up here for some reason. I'm going to circle the invariant points in green. Who can tell me why they're invariant?
When you take the square root of the y coordinates, so the same of 1 and 0.
Right. They're invariant ultimately because, so I guess this is D? D? E? Okay, thank you. For some reason I just didn't put it up here. E, they're invariant because y equals 0 or y equals 1 in those places. I don't think we need to write much more. You know, given the fact that I've already said you take the square root of y, the square root of 0 and the square root of 1 are going to be invariant. And the next question, determine the domain and range. Well, we're just going to look at the graph. The domain is that x is less than or equal to 1. The range is that y is greater than or equal to 0. And I would say to you that in this lesson, in this section, when you're dealing with square roots of functions, ultimately domain and range are typically found by looking at the graph. Don't, it can be found algebraically, but it's complicated. All right, let's take a look at the next example. I guess that whole first thing was, I must have called it a warm-up then, eh? Okay. So this is what I was talking about earlier. You can't put this in, you can't put the square root of something into your calculator because you don't know what that thing is. It's a complex, piecewise, we would call it function. But what we can do is the following. We can say that the square root of this function will contain this point, and this point. The other thing we need to know, and I did this intentionally, is that you have to be careful on exams. When you see an arrow, you need to understand that continues. So if I were to extend this, doesn't matter. This will be invariant, and so will this. Why are those 5 invariant points? Because that's where y equals 0 and y equals 1. You remember those questions where I give you a graph and I say how many invariant points are on negative f of x, and how many invariant points are on f of negative x, and how many invariant points are on x equals f of y, and its numerical response? Well, now I can add another one. How many invariant points are on the square root of a function? And this happens to be 5 of them. The function that I'm drawing, which will be, I'm going to call it g of x, I'll use red. I'm going to call it g of x equals root f of x, where f of x is the black function, will not exist between negative 10 and 2. Which is going to be weird. The graph of this square root function is going to have a single point, a single lonely point over here by itself, and then there's going to be this chasm of nothing, and then the square root of the function will exist. The square root of the function will not exist between negative 10 and 2 because the function between negative 10 and 2 is negative, and function means y, and you can't take the square root of a negative. Now, what will the rest of the graph look like? We need to pick some points to get a flavor for what's going on here. The y coordinate at this point is 4. So we take the square root of 4 and give us 2. Now, you need to be careful about what you're going to draw here. Well, I guess maybe you don't. You should know that from 2 to 4, the graph will look something like that. I mean, I'm going to say you need to be careful because that little bubble where it rises above the graph, you want to make sure that you don't do anything foolish like this. Because it can't go backwards and then forward. It has to be rising all of the time. So it's a tricky little thing. It's subtle. And then it's also going to have a curve here. Resist the temptation to make it smooth through this point at y equals 2. Because the slopes of these two lines are different, the curves will meet at a point. Okay? So what it's going to look like is something like that. That's the function. It will not exist in between negative 10 and 2, and it will not exist past 8. Nada means nothing. So what is the domain? Well, the domain is x is equal to negative 10 and negative 2 is less than or equal to x, which is less than or equal to 8. There are two parts to the domain, and that's the best way that we can write it. X can be negative 10, or it can be any number in between 2 and 8. What is the range? Well, we have to look at the graph. The range is that 0 is less than or equal to y, which is less than or equal to 4. Sorry, to 2. Any questions with 1? Yep.
Is it negative 2 or 2? Or the x?
Thank you. It's 2 to 8. Good eye. Good? Okay. Try another one. Sketch the graph of this function, state the domain and range. Well, right now I can tell you that the domain will be this. And you should understand that because that's the only, this is a weird thing we're talking about. That's the only horizontal location where the graph is vertically above or on the x-axis. With a little bit of thought, you should be able to tell me what the maximum value of y will be. It's going to be root 3. Not put root 3 in your calculator and go 1.73. Root 3. We're in Math 30 here. And honestly, this might be a numerical response question. Given this graph of f of x, the domain is negative a is less than or equal to x, which is less than or equal to b, and the range is c is less than or equal to y, which is less than or equal to d. What are a, b, c, and d? Let's sketch this. And how many invariant points are there? Well, there will be an invariant point here, an invariant point here, one here, and one here. We do need to find out where that peak falls to, which we know it falls to y equals root 3. We do need to throw root 3 into our calculator so we get an idea of what that number is. And that number, I think, is 1.73-ish. Is that right? Thank you. So 1.73 will be around here. What does this graph look like? Looks something like that. That's it. Any questions with that example? Final one, sketch the graph of this and state the domain and range. Well, the domain will be x as any real number. And I want to be careful here. It's not any real number just because the graph lies entirely above the x-axis. It's any real number because the graph lies entirely above the x-axis and exists everywhere. Okay? If I told you that this was the function and there was no arrow there, the square root of that would not be any real number. It would be x is greater than or equal to whatever that x coordinate is. Once again, though, the important point is this graph lies entirely above the x-axis, which means every y coordinate is a rootable number. You can square root it. No. Y will be greater than or equal to some number. The reason it's going to be greater than or equal to, and I'm trying to get you to think outside the box here, meaning in this context, not having to look at the graph to answer the question, not having to draw the square root of the function to answer the question. This original function on the left-hand side goes up forever. So the y coordinate on the original function will always be getting bigger and bigger and bigger, and when you take the square root of it, you're just going to keep getting a bigger and bigger number. I mean, they're going to be smaller numbers than the original, but they as well will continue to climb to infinity. What will be that minimum value of y? Well, it's going to be whatever the square root of the minimum value of the original function's y is, which happens to be invariant. This is going to be an invariant point. And I don't want you to look at this and go, oh, the range is always going to be y is greater than or equal to the y coordinate here. Because if this scale were different, and this were 1, nah, bad example, and this were, 12, that would make the y coordinate here 6, and that would not be invariant. The range would be y is greater than or equal to root 6. But it's not 6, it's 1. What does this graph look like? Well, we have one invariant point here. We have this whole line, which is up at y equals 4. Every point on that horizontal line is at y equals 4. So when we take the square root of 4, we get 2. So that's what it's going to look like. I don't think you need to, you could, pick 2 here and move it down to 1.4. I think it's pretty obvious that this graph will curve up like that. And it's also going to have a similar kind of curve over here. Now, you don't have anything else for context on the left side, so you might want to pick a couple points to give you some scale, I guess. This point is at 4, so if we move it down to 2, that gives us an idea of what we're talking about. So this is what the graph will look like. Oh. Roughly. By the way, that curve looks parabolic, but it's not technically a parabola. And you can see, of course, x is any real number and y is greater than or equal to 1. That is it. If I had to summarize this lesson, it's this. When you go from f of x as a graph to g of x equals root f of x, the mapping tells the entire story. If you understand this mapping, you should know why invariant points exist when y is 0 and y is 1. You should know how to determine where the square root function exists, because you can only take the square root of numbers that are 0 or greater than 0. All of this comes about because of this statement. That's it.